Well, I'd like to thank Peter and Julie very much for inviting us here. It's always nice to be at the Institute. So I would like to sort of talk about the general scheme that lies behind some of the things that Shamgar was saying, and it's a very kind of simple-minded scheme, and it seems kind of amazing that it hasn't gotten more attention. But anyway, so let's talk about it. So the main point is, observation is that classical groups have large abelian subgroups which with the structure of spaces of matrices. Okay, so BG, so you look at GLN, or I'll write it as GLK plus L, and this then contains this parabolic subgroup that looks like GLK and GLL, and this looks like the K by L matrices. So this is the Levy component. It's a product of GLs, and this is the unipotent radical, and it's abelian, and it just looks like the space of matrices. And what do I mean by that? I mean that so it's a module for GLK times GLL, and as a module for GLL, it's the K by L matrices. So the example that Shamgar gave is if you take SP2N, and this all contains similarly a parabolic, which I'll call PN, which is isomorphic to GLN times the symmetric 2 by 2 matrix, symmetric S star of C n. So this equals the symmetric n by n matrices. And well, likewise, if we take split, so ONN, split, this also, I'll call this P prime, and P double prime has also got a parabolic subgroup whose Levy component is GLN and whose unipotent radical is the skew symmetric. N by n matrices. And so if you look at other groups, it's a little more complicated, but still you can typically find some reasonably sized space of matrices inside these groups.
So is it an accident that if in these NN cases,
Yeah.
the abelian thing is somebody else's Lie algebra for the same kind of group?
I don't know. I mean, I don't know if an accident is the right word, but it's characteristic. I mean, the symplectic groups and the orthogonal groups are so intertwined with each other. It's just like, you could, if you only knew half of them, the theory would be incomplete. To really understand their representation theory, you have to think of them together. Okay, so so we have these big matrix groups inside the classical groups, and a second point is that the duals, the vector space duals, of matrix spaces are again matrix spaces. So, for example, if we take the K by L matrices, the dual of that is the L by K matrices. So if we take an S in here and or a T in here and S in here, then we can define lambda sub S of T to be the trace of ST. So so the duals of these spaces are also matrix spaces, and then we can also think of the Pontryagin duals of these things as matrix spaces, because so if F is a finite or local field, or and chi 0 is a character, a unitary character, of the additive group of F, then lambda, then V and V4 vector space, V vector space over F, the dual, the vector space dual, is isomorphic to the Pontryagin dual by by chi sub lambda of V is just chi, or chi 0 of lambda of V. Right. Okay. So then we can think of the Pontryagin duals of these groups as also as spaces of matrices. So the main invariant of a matrix is its rank. So we can attach a rank to, notion of rank to a character of one of these unipotent radicals. Okay, so we can do that. The question is there any interest in it? So I can also notice that, in fact, if I look at irreducible representations, and I guess I'm being a little bit vague about, so certainly unitary representations, but irreducible, admissible representations of these groups of of the parabolic, say P, I wanted to call this, say, PKL. PKL will have spectral decomposition for UKL of consisting of all matrices, all characters of a specific rank. So Mackey theory, or theory of, I want to actually, so let me now just say I'm gonna take the base field to be a finite field, so there's no distracting questions of analysis. I mean, that you can deal with them, and they're not a huge deal, but let's just talk about finite fields. So we're talking about unitary representations and of these finite groups, and then if I take a representation of this parabolic subgroup and I restrict it to the unipotent radical, then it is going to be concentrated. It's the characters that intervene will be the characters of a specific rank, because what rank does in the matrix space of matrices is rank tells you exactly what is the GLK times GLL equivalence class of that element. So so this means that if rho for representation rho of GLK plus L, we can say rho restricted to the unipotent radical will be rho restricted to the parabolic restricted to the unipotent radical. And so each one of these restrictions is concentrated on the matrices of a specific rank. So what we'll get is a sum somewhat similar to what Shamgar wrote down for the symplectic group. So have the rank goes from 0 to the minimum of K and L of some multiplicities times like this. And so, and you can count these orbits. So the number of T such that rank T is R is going to be equal to, well, it's equal to this. It's so this is where this is the Grassmannian variety of R planes in K space. So it's a product. So you, if you have a rank R operator, it has a quotient by the kernel of rank R, and it has an image of rank R. So you get a subspace inside of k-dimensional subspace and a subspace of L-dimensional subspace, and then some linear mapping between them, non-singular. So, and this, if you check it out, so this has size roughly q to the k plus L minus R times R. So it's easy to see that this increases fairly rapidly with R, so that the rank of a representation is related, at least in a loose way, to the dimension of a representation. And the bigger the rank, the bigger the dimension. Okay, so we could define, let's say, so rho in GLN hat has rank. And I'm going to say less than or equal to R if rho restricted to UKL has rank R. And at the moment, I should say, well, take R less than the minimum of K and L. Otherwise, you don't really. Oh, sorry. Right. So, well, let me take. Okay, I'll take the closest I can come to n over 2, and I'll just say rank less than or equal to. So right, n over 2, n plus 1 over 2. Has rank less than n over 2. Okay. So I could take the largest, I take the squarest, huh?
If you wrote n as n minus 1 plus 1,
yeah.
it's a different notion of rank.
Yeah, right. So I mean,
Is this the biggest
yeah, I mean, what happens is that so if the rank is bigger than the minimum of K and L, you don't learn anything by restricting it to K and L. But if it's less than the minimum, then you could learn something. It could be less, right? I mean, so you could test the rank against different K and L,
Yeah.
right? And if the rank is less than the minimum of K and L for one pair, and then that number is less than the minimum of K prime and L prime for another pair, you'll get the same answer. But of course, if the rank is bigger than the minimum of K and L, you can't learn anything. So this, I mean, so your best chance for learning is if you take the most squarest possible unipotent radical. But in a minute, we're gonna go beyond that limitation anyway. So, okay, so I can make this definition. And we can make some observations about this. Some observations or properties of rank. One is that it's if the rank of rho is less than or equal to R, then rank of sigma is less than or equal to S, and R plus S is less than n over 2, then the rank of the tensor product is less than or equal to R plus S. So there's a nice compatibility with forming tensor products. Rank just at worst adds. And maybe another but it seems that in talking about rank that we're limited to roughly half the dimension, half of n, but in fact you can extend this. You can extend the dimension, the definition in the following way. You can observe that. So this, I'll call this A, and B is that if we have GLN is contained in GL, well, is contained in GLN times GLM is contained in GLN plus M. So embedded as part of, on a block diagonal matrices. And rho in GLN plus M hat has rank less than or equal to R, which is less than n over 2, then rho restricted to GLN has rank R. So representations of very big general linear groups, if you restrict them to smaller general linear groups which are block diagonally embedded, their rank stays the same. Their rank doesn't go up when you restrict down. So this allows you to make a more sort of extended definition of rank. Okay, so we can make an extended definition of rank. So we can say that rho in rho in GL n hat has rank less than or equal to R if there exists some very big M such that and a representation, right? And some sigma, say in GLM hat, such that rank sigma is equal to as less than or equal to R, which is less than or equal to M over 2. And rho occurs in sigma restricted to GLN. So I can just look at small rank representations of very big general linear groups and then restrict them down to small general linear groups and see what I get.
If you started with your row and just induced it to some huge group, what would happen to its rank?
I'm going to talk about that. Well, I mean, you can't, if you just induce directly from the small group up to the subgroup, you'll get some huge rank representation. But there's a way to be a little cleverer about that. Okay, so we have this notion, so we have some kind of a filtration on representations, and extend in an obvious way to a filtration on the Grothendieck group of irreducible, of virtual representations, and it has a nice property with respect to multiplication, so tensor product. You get this gives it filtration on the Grothendieck ring by rank, and so what does it look like? It's not obvious that there are any representations of any small rank, but the trivial representation, yeah. So small positive rank, yeah. So the first maybe result is that so there is an injection I don't have a name for it. Well, so it goes from GLR hat into GLN hat R. Given as follows.
R means
Yeah, I guess it's eta. What?
GLN sub R means the Gaussian rank.
Yeah, this is rank R, rank less than or equal to R.
On the back side you have
GLR. Thank you. So I'm taking R again less than n over 2 here. That's to make an injection. So what you do is you form. So you have rho, and then this goes to rho tensor 1 in GLR times into the P R n minus R, which is this group here with a GLR here and a GL n minus R here, and the MR n minus R matrices there. So you just extend by the trivial representation of this piece, and then you induce. So this doesn't pick out an irreducible this representation won't always be irreducible. Often it will be irreducible, but not always. But as in Shamgar's statement, so there's always a unique piece that is not of rank strictly less. As you this, so this in GL n P R n minus R row tensor 1 has a unique irreducible component of rank of not of rank less than R. Yeah. So it's pretty easy to check that this guy will have rank at most R, and then there's one piece that does have rank R and other stuff is less, sort of. Huh?
Did you mean rank equal to R?
Not of rank less than R. So yeah, there's one piece of rank, I mean, there's an irreducible piece. So I haven't defined equal to, right? I mean, it's... yeah, so there's a reason for that, actually, which I should say at the moment. So... so what this, I mean, so the rank is only inducing a filtration on the dual of GLN. And because, of course, I mean, when you take a tensor product of two representations, it will break up into a bunch of pieces. I mean, all those pieces will have rank less than or equal to the sum of the two ranks of the factors, but some of them may have pieces strictly less. So when you worry about the algebra structure, the rank is not, I mean, you can grade the growth and deep group by rank, right? You can say, okay, these guys have rank 1 and these guys have rank 2 and so forth. You can grade the growth and deep group by rank, but you can't filter it as a ring by rank. You have to use you have to filter it. You can't grade it. But you can pass to the associated graded. And then, so a corollary of this is that if we let n go to infinity and pass to the associated graded ring, then we get this situation that GL infinity is equal to a sum from n equals 0 to of GL, sorry, this is hat, GLN hat, and then this has a multiplication, so the induced multiplication of growth and decrings is the multiplication considered by Zelevinsky I don't have the reference written down, but anyway, Zelevinsky quite a long time ago I think in the early 80s, he considered, well, first he considered the direct sum of all the growth and decrease of all the symmetric groups. And then he also did the similar thing for GLN, and he showed that they had a structure of Hopf algebra, of which, so this was the multiplication part of the Hopf algebra, and then there's a co-multiplication given by restriction for GLN to GLN, GLK plus L to GLK times GLL. And I think when Zelevinsky did this, it seemed like some kind of, seemed slightly bizarre, artificial to put these all together in, to take the sum of all these things over n. But that's in fact what you get if you just take the dual of GLN and you consider rank and you grade it by rank and you pass that n go to infinity, then these structures are all stable as you go out to infinity, and you get exactly Zelevinsky's structure. So this has actually sort of appeared in the literature in that kind of a disguise. And I'll just conclude with one last fact that I'm not completely sure of, but it seems to work out. Is that if I'm so Lustig has given a classification of the representations of finite reductive groups, and in particular for GLN, well, for GLN, they had been classified earlier by Green, but Lustig gave sort of a new parameterization in terms of conjugacy classes in the Langlands dual group. And the Langlands dual group for GLN is just GLN. So maybe I should make this a remark and put a slight question mark, but it appears that representations of GLN of rank less than or equal to something are those that appear in induced from GLR again with GL n minus R MR n minus R. So you take the induced again from row tensor 1 from PR n minus R up to GLN. So the description of the rank whatever representations of GLN appears to be uniform for R all the way up to n. For R less than or equal to n over 2, this map is an injection. And for when R becomes larger than n over 2, some of the representations of that you get this way will actually have rank strictly less than R. So there's some kind of condition on the size of the representation of GLR. I think what it is that the representation should be at least of size, is it 2R minus n? The rank of the one here, piece here, should be at least 2R minus n. I have to check that out.
Is this remark based on the classification of Lustig, or is this something you proved?
This is the Lustig, yeah, based on the Lustig parameterization. If I understand the Lustig parameterization correctly, this statement is true. Yeah, yeah. So so there's a similar theory for all the classical groups, and the rank that Shamgar defined for the symplectic group can be extended up beyond n, and in general, and generally speaking, the generic representations will all be of the largest possible rank, which in this case is n. In particular, all the cuspidal representations associated to tori will be a rank n. So those are where all the big representations lie. But the representations should continue to get larger, roughly speaking, as the rank increases. But again, that's not strictly the case, because so in this construction over here, I mean, the dimension of this representation, what you can check is in this construction here, the multiplicity of the rank R characters of this group here, the multiplicity with which they appear will be the dimension of rho. So the rank, there can be a substantial difference in the size of the representations of a given rank, because you have a substantial difference in the size of the representations of GLN, but generally speaking, the rank tends to grow. I mean, the size tends to grow with the rank. Yeah. So that's anyway. This is so there's the picture somewhat like Shamgar described for all the classical groups, and it seems like for GLN it's the simplest to describe, and this this seems to be what it is, and it has in some sense already appeared classically in the work of Zelevinsky. Okay, thank you.